Hello everyone! In this video we're going to be talking about two-dimensional arrays. In our last videos we were talking about one-dimensional arrays, even though we mostly just called them arrays. So here's a quick reminder. This is how we can visualize a one-dimensional array. An array is a collection of values, where each individual value is stored as an element of the array that we access using the array's indexes. So using the correct index, we can find the correct element of the array. And they tend to run in contiguous space. So the first element is here, the next element is right next to it, so on and so forth. We know how to declare an array of one dimension. We start with a basic data type. We have a name for our collection and a size in a set of square brackets. We also know how to initialize an array of one dimension. We use a for loop that goes through all of the valid indices from 0 to size minus 1, indexes each value of the array, and assigns it a specific value. So all we have to do is take these ideas for one-dimensional arrays and expand them to 2 dimensions. Here's a visual to get you started. A 2-dimensional array is more like a grid structure instead of a line of elements. We can put an element of the array in each box of the grid. And so now instead of having one size, we're going to have 2 sizes. And instead of calling them sizes or lengths, there's going to be the number of rows and the number of columns for our data structure. So when we declare a 2-dimensional array, we'll still use one of our basic data types, integers, floats, characters, or doubles. We're still going to give a name to our collection, but now we're going to have 2 different sizes, one for the rows direction and one for the columns direction. So if we were to make an example grid, we could populate it with integers with 3 rows and 4 columns, and it would look like this. 3 rows, 4 columns, and each box can hold 1 integer. And if it takes 1 for loop to populate a one-dimensional array, how many for loops do you think it takes to populate a 2-dimensional array? It takes 2. Our goal, if we're going to initialize a 2-dimensional array, is to visit every possible element. So each square in the grid needs to be visited once so that we can assign it an initial value. To do this, we're going to use a set of nested for loops. So we're going to have our array. It's our grid with 3 rows and 4 columns. We're going to have our 2 counters, I is for index, J because it follows I in the alphabet, and then we're going to have our 2 for loops. One of those counters is going to be for the rows direction, and one of the counters will be for the column direction. If we're just initializing, it's not terribly important which direction we're using as the outer for loop, but it might when we're printing it out, so we'll do a couple of examples later. In this particular example, we're letting I go in the rows direction and J go in the columns direction. So when we set up our first for loop with I is going to take on each valid value for the rows. There's 3 rows, so our rows are indexed by 0, 1, and 2, always starting at 0 and going to size minus 1. So we'll let I start at 0, and we'll continue as long as I is less than 3. Which means J is going to go in the column direction. And there are 4 columns, so J will start at 0 and go as long as J is less than 4, so that J will hit all of the valid column numbers, 0, 1, 2, and 3. And at each iteration, we're going to go to that spot of the array, the ith row and the jth column, and set that element to whatever our initial value is. In this case, it's 0. So what is essentially happening is that our outer for loop controls which row we're on, and our inner for loop marches across that row to set every value in the row equal to the initial value. But we could also do it the other direction, where we're doing our columns first, and we visit each column and set each value down the column equal to our initial value. And that would look kind of like this. The first part's the same. This is our grid. It's got 3 rows, 4 columns. We've got counters I and j. Now we're allowing I to go in the columns direction. Since there are 4 columns, I will start at 0 and go strictly less than 4. And j is now for the rows direction. So j will go from 0 to strictly less than 3, since there's 3 rows. What's important is that we put the right counter in the right spot. It's always row first, then column. So since j is going in the rows direction, j goes in the first box. And when I is going in the column direction, I goes in the second box. When we did it the other way, if I is going in the rows direction, I goes in the first box. If j is going in the column direction, j goes in the second box. It's always row, column. So that's a good way to think about two-dimensional arrays. It's a row-column structure. Always row first, column second. If you're used to thinking about Cartesian planes, you can also think of this as yx. First, we go in the vertical direction before we go in the horizontal direction. So row first, then column. So as an example, we'll put some values into our grid. We're going to go to the second row, the third column, and put the value 4 there. And if we did, it would look something like this. Here's our two-dimensional array with the 3 rows and the 4 columns. And if we go to the row indexed by 2 and the column indexed by 3, we're going to be in this box over here. And we can put a 4 there. So let's look at a few more examples. In this case, if we wanted to go to the row indexed by 1 and the column indexed by 2, that would put us here. And we would put a 5 into this box. The first box is the box indexed by the 0th row and the 0th column. Remember, in computers, we start counting at 0. So this first box here is box 0, 0, the 0th row and the 0th column. If we wanted to go to row 0, column 1, that would put us here. We could put a 2 there. So we could fill all of our values this way, or we can use those for loops where we let I range in one direction and j range in the other direction. So let's look at an example that doesn't necessarily have zeros in it so that we can see how it's working. This allows I to go in the rows direction and j to go in the columns. So 3 rows, 4 columns, strictly less than 3, strictly less than 4. And we'll say the grid at the ith row and the jth column is equal to I plus j plus 1. And we'll trace that and see what it looks like. So we're going to take these out for now, and we're going to take these out of our array so that we can start from the beginning. We'll assume that it's declared but not yet initialized. This will be our initialization. Okay, so now we're going to trace our for loops. We'll start here. So I is equal to 0. 0 is less than 3. So we'll execute this for loop. Start j at 0. 0 is less than 4. So go into the grid at 0, 0, and put 0 plus 0 plus 1 there. Okay. J will increment to 1. 1 is less than 4. So go to our grid at 0, 1, and put 0 plus 1 plus 1 there. Okay. J will increment to 2. 2 is less than 4. So go to the grid at the 0th row and the column indexed by 2 and put 0 plus 2 plus 1 there. Then J will increment to 3. And since 3 is less than 4, we'll go to this spot of the array and put 0 plus 3 plus 1 there. Okay, so then J will increment to 4, and 4 is not less than 4, so we're not going to run this again. Instead, I is going to increment to 1, and 1 is less than 3, so we're going to repeat the inner loop, which starts J back to 0. So now we'll go to the 1 row, back to the 0 column, and put 1 plus 0 plus 1 there. Then J will increment to 1, and we'll march across the row again, putting in values that are I plus J plus 1. So hopefully we can see what the pattern will be. When I increments to 2, we'll mark across this row, the row indexed by 2, and do I plus J plus 1. So that we've filled our two-dimensional array with initial values. So we're going to take these ideas and build a multiplication table, which you might remember from grade school. So now we'll note what our columns are. And we'll try to get one for the rows too. Okay, so this should help us keep track of which row and which column we're dealing with. We've got rows 0, 1, 2, 3, and 4. And columns, same number, 0, 1, 2, 3, and 4. So this will be 5 by 5. So we know that if we were to multiply 0 by 0, we would get 0. Now if we multiply 0 by anything, we'll get 0. Same here. So this part of the multiplication table is easy. And so the rest of the boxes we fill in with the multiplication. So this one will be 1 times 1, 1 times 2, 1 times 3, and 1 times 4. Pretty simple. So it'll be 2 times 1, 2 times 2, 2 times 3, 2 times 4, the 3's for multiplication, and the 4's. So if you're trying to build a program to help somebody out with their multiplication tables, we could build that using a two-dimensional array. So that's what we're going to do for our example. We're going to come over to Code Blocks. And build a program with a two-dimensional array for our multiplication table. And if we want to, we can skip the 0 parts because we know that 0 times anything is 0. We're going to make it so that it'll be easy to modify the number of rows and the number of columns later. We're going to start with just multiplications up to 5. So we'll do 1 through 5, and I believe grade school goes up to 12. So we'll do a 5 by 12 to start off with. And as always, having these as constants makes it easy for us to change this later, and we only need to change it in one location, which is right here. So when we declare our multiplication table, we want it to have the rows number of rows, and the columns number of columns. So the two sizes are rows and columns from our constants. We're also going to need our two counters, and that might be enough. So first, we need to create the table. So we'll do the same thing that we did in our other initializations examples. We need to march across the rows and set each value in the row equal to the value that should be part of the multiplication table. So we're going to let I be our counter for the rows direction. So we'll start it at 0 and go strictly less than rows. That makes J our column counter. So we'll start J at 0 and run J less than the number of columns that we have. And then at each spot of the multiplication table, we need to do a multiplication. So if we're going to skip 0, we need to trade out our 0-based numbering system, meaning a system that starts counting at 0, for a 1-based numbering system, which is what most users are used to seeing. So before we multiply I and j, we'll add 1 to them, so that instead of multiplying 0 by 0, we're starting those values at 1. Then we need to be able to print out the table for our users. We want to be able to show them kind of a header so that they can see which values are being multiplied. We're going to try and print out the top of the header first. So that will be all of the numbers that we're multiplying, which are 1 through 12. So we're going to have I start at 1 and go until it's equal to 12, but not greater than, and print out the value of I each time. We're going to go ahead and make sure that this looks okay before we continue. That looks good. Okay, so then we're going to be able to print out the table going down. We're going to want to add in front of each row something that also indicates which value we're multiplying. So we've got 1 through 12 across the top. We're going to need 1 through 5 down the side. So the first thing we'll do for each row is print out that 1, 2, 3, 4, or 5. So that'll be I plus 1. So there's 5 rows, so normally I would be 0, 1, 2, 3, and 4. If we add 1, it'll be 1, 2, 3, 4, and 5. Then we can print the contents of that row. And we're going to try and preserve the spacing that we've got, which is just 4 spaces between each number. And we'll get this value from the table at row I, column J. And then at the end of the row, we'll want to print a new line so that we can go down to the next line for the next row. So let's see how that is looking for us. Oh, our spacing got a little off. Okay, so we fixed all of the formatting issues. Let me walk you through what I did. Since some of our numbers have 2 digits and some of them have 1 digit, the first modification was to make it so that each value takes up 2 spaces. This is a piece of syntax formatting that we use similar to the one for controlling the number of decimal places. We place a value between the percent and the character code for the percent code, a value of how many spaces we want that value to take up. So in this case, this takes up 2 spaces. Then, because we're printing a number at the very beginning of the row, the number of spaces between that indicator and the first value is 1 less than the space we put between all other values. So if we do it this way, and these are just formatting issues, the table still prints fine without them. But if we do it this way, then our table prints out nice and neat, and we can see all of the values and all of the multiplications. So if we want to know what 5 times 7 is, we can find that intersection to see that 5 times 7 is 35. And if we need to know what 3 times 12 is, we can find that intersection to see that it's 36. That's how the multiplication table works. So another thing that we can do is print our table out going the other way, where the short part, the 1 through 5, is across the top, and everything goes downwards. So let's try that. We're going to keep all of this because it looks nice. We'll build a second version that prints out columns first. So we'll print out the header. This time we're only printing out 1 through 5 for the rows. And we'll print out a new line to get ready to start the table. The primary difference that we're going to see is the controls for the inner for loop versus the outer for loop. Now we want the outer for loop to go in the column direction and the inner for loop to go in the row direction, which is the opposite of what we did before. There's a couple of schools of thought on this. You can dedicate I to be in the rows direction, meaning this outer loop would now be with J. Or we can dedicate I to being for our outer for loops. I'm going to try that one so we can see what it looks like. Now the outer loop goes in the columns direction. At the start of each, we're still going to print the very first values. And from our multiplication table, we're printing the very first value in the ith column. So we're going to go to the ith column and print out the very first value, which is in row 0. So row, then column for our indexing. So the first element of the column is in row 0 for the ith column. So now J is going in the rows direction, and we want to print out row, then column. So J, then I. J goes in the rows direction, so J goes first, row first, then column. I is going in the column direction, so I go second, row, then column. And then we'll want to print out a new line before we start the next printout for our output. So again, depending on our specific implementation, we'll make a couple of formatting changes so that when we print the table, we have something that looks clean and looks like a multiplication table. So same process as before. If we wanted to know what 4 times 10 was, we'd find the intersection of 4 and 10 and see that it's 40. So the data in the background is stored the exact same way for both, but our printouts has been different. We can print either rows first or columns first, depending on how we want that output to look. And that's pretty much it for the material on two-dimensional arrays. They're exactly like one-dimensional arrays, except now they're more like a grid structure instead of a line structure. Instead of having one length, they have two sizes, the number of rows and the number of columns, but they're used the same way. If we have an integer array, we can use an element of the array, whether one-dimensional or two-dimensional. Anywhere an integer can be used. We can read information into them the same way. Get an integer from the keyboard or from a file stored in the element that we would like to put it in. The major difference that you'll find is that two-dimensional arrays are almost always used in programs that also have functions, which is what we'll be talking about next chapter. See you then!